Okay, so there are 2 points missing. First is, what do we choose as an elementary process or elementary step for which we calculate these energies? And I think we already discussed it in other lectures. So you could have AB exchanges. On random sites. Could be AB exchange on neighboring sites. Could be A or B vacancy, exchange, so atom jumps into a vacancy. And finally, it could be, I would call it transmutation. You can transform an A into B and a B or a B into A. Sorry, of course the second one should be the other. Not today, but tomorrow I will show examples where it becomes important. At the moment, since we are still just in equilibrium, it does not matter which one we take, except for the last one. There it would matter, but there is also an interesting option. If you are studying equilibrium properties, probably the first one is the best because it does the strongest intermixing of the configuration. So you're not stuck in one local minimum or so, but have a more homogeneous exploration of the configuration space. On the other side, if we are doing kinetic Monte Carlo, so studying the evolution towards an equilibrium, this is a bad choice, the first one. The second one is a moderately bad choice, and probably, I mean, depends on what you are looking at, but probably the third one is the best. When is this fourth possibility of interest? The first three ones, they conserve the composition. So they are in a canonical ensemble. Here you change the composition, so it's a grand canonical ensemble. And I will show that this is a very easy way to calculate phase diagrams in Monte Carlo. Yeah? Now you give, or in this case, you give a chemical potential or chemical potential difference of the two species, and then automatically the composition adjusts to this choice of the chemical potential. Then you get after a while you get a graph of chemical potential versus composition, and from this you can derive the phase diagram. Oh, this is for phase diagrams. Or other cases where the composition is not fixed. Yeah, that's just an example. This is for equilibrium properties. And these are mostly for kinetic. Like precipitation kinetics or so. Okay, so, and then how does it really work, this machinery? Let's do it, for example, for an AB exchange. First step is you choose an AB pair. Then according to one of these possibilities, you calculate the transition probability. Yeah, I call it C1, C2. C1 now is the AB pair in its initial position. And C2 is the AB interchanged. And now it's where the randomness comes into the play. You draw a random number. Between 0 and 1. And you do the exchange. If this pi is larger than r, you don't do it. If this random number is is larger than and this you do so many times until you are satisfied. So the what? Rando. Rando is a family in Germany. Thomas von Rando and ministers and so on. Quite prominent family. Yeah?
Another question there. So like when we are calculating the transition probability, that is the pi value,
Mm-hmm.
C1 to C2, we are using the expression of the potentials that will be used.
Yeah, I will show a very simple way to calculate these energies.
My question is that if I interchange a A and a B,
Mm-hmm.
randomly interchange a A and a B, now while calculating that potential for the initial configuration and final configuration, do I only consider the neighbors of that particular point, or like do I consider the entire system? Like while calculating the interaction, do I include like all the interactions, or like just the first NN neighbors, or
That's a question of how much computer time you have and how much reality you want to have in your simulation. You can do as you like, yeah. And the simplest case, I think I have it somewhere here, is that you just take nearest neighbors. So this energy, as in MD, you need a kind of model for your energy. And the very simplest, it's a counterpart to Lennard-Jones, perhaps, is nearest neighbor interaction. Sorry, there's no comma. Nearest neighbor and only pairwise. So this is one possibility. With pairwise interaction, you can go to higher neighbors. but still pairwise. Even more complicated that you go away from this pairwise interaction to triple, quadruple, or whatever you like. And I will show an example in one of the forthcoming lectures for the third one. This allows to make rather realistic modelizations. Yeah? There's a nice procedure called cluster expansion. And there's also a software tool which allows to generate the input data, which is abbreviated ATAT, Alloy Theoretical Automatic Toolkit, which derives these necessary parameters here.
Another question is that the given algorithm that is being followed here, the Monte Carlo, so that is the metropolis algorithm only?
This depends which one you choose here.
No, because if I go up, so in the procedure, like we choose a pair, then we...
I mean, here, yeah, for this example, I just used this one here, yeah. AB exchange, but this is one choice, yeah.
So suppose like I am calculating, my point is that before calculating the transition probability, which is going to be like exponent of minus some term minus exponent of some other term. So
not really. Exponent of the energy difference over KT or so.
Exponent of energy difference, like EV minus EA or something like that. But before doing that, I should be actually just calculating the energy that is there in the final state. And suppose if it is lower, then I should anyways accept that too.
No, that's not necessarily the case. I can also, this is the first one here. The first one is where you always do the exchange if the energy goes down, and you accept the exchange with a Boltzmann probability if it goes up. But here, in this case, you do both with a thermal probability here. This one here. Here you have a factor which is different from one, and here again. By the way, here one has to be a bit careful. I remember that I once made this mistake also, I think. If you do, as I proposed here, you do the exchange if the probability is larger than a random number. And you have random numbers between 0 and 1. One of these is larger than 1, one is smaller than 1. Yeah? So in one of the cases, you always do the exchange. And then you have a wrong factor of 2 in the denominator here. Yeah? I mean, this one here, let me see. It looks like this. That's this first algorithm here. And the second is supposed to be something like this. But if you choose random numbers between 0 and 1, it cuts off here. So then you end with this one. So to avoid this, you have to choose random numbers between the largest, between 0 and the largest possible change in energies. Yeah, that's a small complication. Yeah, and here you should be careful. Here it's similar, but here the complication is somewhat different. I think Guru will come to this point. If you use a large saddle point energy, which is typical, then this very often will be small numbers. So you will have many, many unsuccessful attempts here. Yeah? So the saddle point energy can result in a huge waste of computer time. But there is a way out of it, which is quite nice. I mean, basically, since this saddle point energy, we keep it constant here. It just rescales the time. Okay? Yeah.
So when we say metropolis, we mean the transition probability algorithm that is given by A. How you choose to exchange is where Glauber, Kawasaki, all this come. That is one. Second thing, even in the case you are using EAM potential, for example, even then you don't calculate for all because there is a cutoff distance. Right? You are using LJ, there is a cutoff distance. Yeah. So even in an off lattice, when you do more complicated energy, it is never the full system energy. Even if I randomly exchange, it's only to the region where energy will change. But because now we are discussing on lattice things, you can do all the bond energies and everything can be in terms of bond energies. But some of the LAMPS implementation of MC, if you are using EAM potential, will do energy, but will do energy up to the cutoff.
Yeah.
That is something.
Yeah, I did not say this. I assume tacitly that we are working on a rigid lattice here. And of course with finite range interactions. Huh? And perhaps I very briefly sketch a simple situation. For this first case, you have A atoms and B atoms. And if you assume next neighbor pair interactions, you would have an epsilon AB here. You would have an epsilon AA here. And you have an epsilon AB here. And then if you choose a pair for exchange, say this one here, then you can very simply calculate the energy change, the delta E. This pair exchange energy times the change in number of AB pairs. You can reduce all the other, I mean, the total energy is the number of AA pairs times epsilon AA plus the number of AB pairs times epsilon AB plus and so on. And this boils down to this simple expression here if you have exchanges. So the initial energy, in this case, would be, and this is how I used to implement this algorithm. So this is, no. Oh, okay. This in B or in A and B denotes a number of A or B neighbors of site I. So the initial energy and the final then becomes epsilon z mean minus NB1. These are very simple calculations, and this is epsilon NB of psi 2. And then so this is atom 1 here. This is atom 2, which I plan to interchange. So the energy difference with few intermediate steps So this is what you basically in a code implement. This is or what you have to calculate. In the simplest case, you choose atom 1, you choose the number of B neighbors here, you choose atom 2, compute the number of B neighbors here, takes the difference. This gives you the energy difference. Yeah? Or, which is even more efficient, but a bit more complicated, you keep track of all the neighbors of a given lattice site, and then you have this table of neighbors. You just have to take it from your table here.
Here the energy epsilon is
This is pair exchange energy.
minus
I think it's epsilon AA, epsilon AB.
minus half of EAA.
I'm not 100% sure whether it's this or multiplied with 2.
Yeah.
I would have to check because once in a while or during the last 20 years I use switching back and forth between these. So that's the simplest way you can implement such an algorithm. And we uploaded my simple Monte Carlo 2D scripts or programs here. I can very briefly show you. I don't know whether you're familiar with Fortran, but most things are easy in whatever language. So this is just the initialization. The comments are in German, I apologize. So that's the initialization of this 2D lattice on a square lattice here. This is some plotting arguments here. Here. What? Hmm?
Can you zoom into it?
Yeah, sorry. Like this? Here you calculate the initial energy and set up this number of B neighbors and the periodic boundary conditions. This, I think, is the Monte Carlo loop. Yeah? So you choose two atoms, I and J. Here I use just one, and then I choose a neighbor. And then I choose whether it's a left, right, top, bottom jump. And then somewhere is here, this is this basic line that you take a random number and check whether it's smaller or larger than the exponential of this delta E. The delta E was calculated using this change in AB pairs. If this is the case, then you do the exchange, otherwise you don't. That's basically all. The rest is some evaluation. Perhaps I say a few words at the end also about the random number generators. At this time, when I started these works, it was quite a complicated thing. Today it's much easier. But that's the basic algorithm, and I can show you. And we can do it. I put this pair exchange energy to 1, and then it's only, because only epsilon over kT enters the calculation. Yeah? It's only this ratio, then I can vary the temperature. So I use 0.5 here as a concentration, blue and yellow. I think Guru already showed this example. We can use a high temperature. Here, everything is jumping back and forth. Nothing happens. Now I can lower the temperature. And very rapidly, it's ordering. And for a short instant, you saw an antiphase boundary where the ordering jumps, but nothing persistent or so. You can go up again, homogenize, and perhaps small here it's still disordered. So I try to register the order parameter here. It's still, if you look here, it's still close to 0. I think here it's already ordered. Not really. Here you see kind of metastable domains which form here. Yeah? Here, for example, here are domain boundaries, but they disappear after a while. Yeah? And here now, here you see a domain boundary, I think. But since it's a second order transition, there's no metastability. And the same on a triangular lattice. I take a concentration of 1/3, and I plot only the B atoms. And the B atoms on the triangular lattice can occupy 3 different positions, crystallographically non-equivalent. The left corner, the right corner, or the top of the triangle. Yeah? So I choose 3 colors according to on which sub-lattice they sit, the B atoms. So these 3 colors, they all denote the B atoms, but sitting on different sublattices. So again, we can start with a high temperature. You see that all 3 colors are equivalent. There's my mouse. Now I can lower the temperature. Here you see this short range order, I would call it. Yeah, it's not a stable. Now it starts to order, but it takes much longer time. You see this metastability. And perhaps I go a bit deeper in temperature. Now you see these different domains of ordering. One can make bets which one is winning. Probably the blue one. You see the periodic boundary conditions here. But it's very stable. Yeah? And overall, the degree of order is close to 0 because all 3 domains more or less have the same area. Huh? Only after very long time you will really reach an equilibrium state. Yeah, now the blue is starting to win. Huh? So if you wait a bit, the green has disappeared and then the blue as well. So it's a basic difference to what happens on the quadratic lattice. Yeah? Here now it's done. Still you see that some atoms hop around. It's not that everything is frozen or so. Yeah? They are just changing between the sublattices, but they prefer to stay on this majority sublattice now. And if I would start with other starting conditions, it could be the green or the red domain which wins. You can do the same. I think I already showed this in the introduction for a precipitating system where the epsilon has a positive sign. So if you put 10%, for example, here, now I plot both species. Orange are the A atoms, blue are the B atoms. And at high temperature, 2 or 3, everything is homogeneous. Now BB and AA pairs are preferred, and AB pairs are unfavorable. Huh? So nothing happens. If I go down in temperature, you see some pre-clustering, but not yet stable clusters. And here the precipitation sets in, some nucleation, and perhaps I go down a bit. Now you see that stable clusters formed. They exchange atoms between each other, and after some time the small ones disappear. That's the Ostwald ripening. The big ones stay, and if we would wait long enough, there would be one huge blue particle and all the others would have disappeared. And this is this very simple implementation, just with AB pairs and nearest neighbor interaction and pair exchange. Of course, this is only a model system. It's not a realistic description of something, but we could also do it for higher concentration. Point 5, where you would expect spinodal decomposition. Here there's some tendency to form BB pairs, but not very pronounced. And now, the lower temperature, you see this formation of such a spinodal microstructure or whatever. It's a coarsening of this structure as well. I'm wondering whether the blue structure is interconnected and the orange not.
Yeah, blue looks like.
But maybe that's just also a misinterpretation of our, I don't know.
We can teach partial fulfillment.
Yeah.
One of the later lectures.
Right, yeah. So perhaps as a last point I wanted to make here, you see this algorithm which I explained, is about the random numbers. How do we generate the random numbers? And I think Guru already said some words. One way would be to use real physical random numbers. Yeah? One could use, at least on Unix systems, there is a pseudo device, devrandom, which generates random numbers. I don't know what they really use, some address or so, which is fluctuating sufficiently. But that's not a good idea for two reasons. First, I think it's not very fast. Second is, normally we like not to have real random numbers, because if there is some mistake in the code, it's good to run the code again with the same starting conditions. So we have to use pseudo-random numbers. And one way to generate pseudo-random numbers is this what is it called? Congruential algorithm. Somewhere I had a page on this. I don't know. I deviate too much from this script here. I need my notes because these are huge numbers which I use there. Yeah. So, Guru already said, in typical Monte Carlo runs, we can have a huge number of iterations, like 10 to 9 or 10 to 10 or so. And you must guarantee that the sequence of your random numbers does not close, so to say. Yeah? So, it's worth to choose good generators. Pseudo and typical algorithms use this iterative procedure. You have a random number Rn, you multiply it, you add something perhaps, and take the remainder by division by C, so the modulus. The best is if you choose A, B, C large prime numbers. And in many algorithms, B equals 0, so this B is just thrown away. And for these prime numbers, there are good candidates. One type of, they are not all prime numbers, the Mersenne numbers. To power another prime number -1, I think. These are not always, but often prime numbers. And one possible choice is this is even not a prime number for A, but apparently it does not matter, and B equals 2 power 31 minus 1. So that's a common generator not that good. Nowadays there are better ones. I think the one I used in this little code here, I have not noted here. Here you see the period, but oh yeah, okay, I think this is 2 power 31 minus 1 here, this one here. And the multiplication is, in this case, is done in 2 steps because it's old code. But better ones are so-called Mersenne twisters, not sisters, but twisters. As I choose a Mersenne number 2 power 19,000 something. And then they draw a certain number of these in the sequence here. No, 624. And they are shuffled. And there are more algorithms. So, as Guru said, it's very important to check the properties of a random number generator if you are not convinced that it is a good one. And I think here on my, here I showed how one could check. Here using this def random source of random numbers, I generated 1,000 random numbers and calculate the autocorrelation function, which is very peaked here, so it's not too bad apparently. There's no correlation visible, but if you would generate a larger sequence, perhaps you get a correlation and the Fourier spectrum of the correlation function. And here's some words. I think, did you already show this one here? That in the past, very bad random number generators were used. I mean, this is from 76, so they had a period of only 8,000 something. I don't know whether you know the PDP computers and the IBM computers. IBM is still known. So there is a real lack in randomness here. And here's another article, not that old, from 86. And here in this paper they discuss the pros and contrasts of different random number generators. The one I showed here is this multiplicative congruential generator. There are other ones which are as well working fine. But also an important point, like in MD, most of the time of simulation is spent for the potential calculation. Here in MC, most of the time is spent in the random number generation. Yeah? Depends, of course, how much other things you do, but it's really worthwhile to choose a good generator on the one side, but an efficient one on the other side. So I think this is all I wanted to say about Monte Carlo today. Yeah?
What visualization software was used?
Which?
With the Fortran scripts?
I used this from this source here, which was claimed to be very good. It's I think it's a 30.
Visualization.
The visualization. This one is a homegrown visualization I wrote also more than 20 years ago, 30 years ago. Very both sides simple and how do you say, elementary. I don't know whether you're familiar with X11, the graphic system on most Unix systems until nowadays, and one can address directly these basic routines. I can show the code here. So here's all the graphics primitives. Here's the initialization. Here you draw a line, you draw a point, you draw nothing, you put a color onto a region, you draw a circle, and so on. So this is, but it still works. I mean, you have to have the X11 developer libraries. And if you compile or if you link the code, you have to give this X11 library, and then it works still. I myself was astonished. I did not touch this code for a long time, but still. An advantage of these primitive things is that they are typically fast. In some of these routines, I think I even put some delay of something to make it evolve not too fast, because in these simple systems it's very fast on nowadays computers. I think I also uploaded this one to, yeah. So if you like to play, and if you have some Fortran capabilities, you can easily play with these codes. It's extremely simple.
Fortran and this C,
This
both
is-
are compiled together.
Yeah, this is very simple to compile. I can hope it works. You can even compile it with a C compiler, because it's all the, no, you can compile the C with a Fortran compiler, because I think it's interchangeable. It's all this GNU compiler system. Let me try this one. And here at the end you have to give this library X11. I hope it works. Okay, there are two warnings, because somehow this Fortran syntax changed a bit over the many years, but can check. Yeah, works. So, if you like to play with this graphics library, we developed it, as I said, long time ago in the early 90s, I think, because we had some electron microscopy simulation software and no way to visualize our simulations there. It was the starting of Unix, or not the starting, but early times of Unix workstation, and all these graphics tools were not available as they are today. Today, of course, it would be written in Python or something like this. Okay. Good.
Okay. So I'm going to do two things today. One is that the Monte Carlo is the very first set of scripts that we wrote on the very first day. But I know that most of you are interested in using Sparks. We haven't used Sparks as much as we have used LAMPS, but still, thanks to Nagarajan, we have the ability to work with Sparks. And so I have taken one example which is already there in Sparks. I don't know if all of you could load Sparks on your computers, but if you have Linux, it is not difficult. I did load about a week ago, and it is simple download. I think my Sparks
loading is somewhere here. Yeah. So, you download and then you go to the source, and then there is make serial and make parallel, make MPI I think, yeah, make MPI, and it produces. And last time I also managed to compile it as a library. Okay, I still haven't fully put it together, but I now know even how to do that part. So, if it is a Linux machine, it is fairly easy to do this, and once you have the executable, you just need to put the executable in the same directory, you put your in file and you can run them. And as you would see, one of the nice things about Sparks is that the in files are not too different from LAMPS files. If you are used to LAMPS, they look very similar. One problem I did find is that Sparks documentation is very poor and there is no consistency. The download page might say something, the readme file says something else, and the manual says something else. So, I did make several mistakes, and finally, I did manage to get something working. For example, yesterday after a little bit of effort and then finally, I gave up, I sent a mail to Nagarajan asking him to share with me how to write the data files and visualize. And by the time Nagarajan shared this morning, I already figured out for ParaView. Okay, so, today you get to see both ParaView and Ovito. Ovito thanks to Nagarajan, and ParaView that I figured out myself. So, it takes a while to do things because the documentation is very poor. In one place you do not see all the information you need, and unlike LAMPS you do not have good example files. I am hoping that we will correct some of it with this workshop. What we do here will become available online also for anybody who is doing. So, with explanation and with some notes, typically I use knit R to generate documentation. This is from a philosophy called literate programming. I do not know how many of you know about this. There is this program called TeX, which was completely written in a programming language or software you can say nowadays, written to write this software. And the program is written with the philosophy that into a machine you can give the program in whatever format you want. As long as there is no syntax errors, machine will run the program. But it is very hard for a human being to read that program and understand. So, Kanuth had this idea that you have to write programs which should be mostly text meant for human beings. And there will be code parts which will be there, which there will be a compilation, this thing you do, you put together and it will come as a code separately. And he wrote this books called TeX books, I think some 3 or 4 volumes. All of them are written using this, so he called it as knitting. I mean, you take the comments, and this is documentation of extreme levels, right. I mean, there are pages and pages of documentation and few pieces of code, which is something I find useful. For example, I teach this course on data analysis and interpretation, and it so happened that today morning we did calculating pi using Monte Carlo simulations, because I was teaching them bootstrapping and simulation. So, this is what my code looks like. So, when I compile, I get a PDF file which has all this information, which explains what the code is and what the plots look like and things like that. But you can execute pieces of code. For example, this pi value calculation by doing simulation where you do 10, 100, 500 and so on, and for every these are the number of random events that you generate. I hope you know how to calculate or evaluate an integration using Monte Carlo. So, those are the number of Monte Carlo steps that you are taking to integrate, and then you can just run the chunk of this code. So, initially it is off, you do 10 times or 100 times etc., but by the time you come to some 400,000 or 500,000, you have converged to the pi value. Okay. This is by throwing random dots at a circle which is within a unit square, and so the ratio of number of points that lie inside the circle to the total number of points basically gives you the area, and hence you can divide by the r squared and get the pi. So, that is the code. So, I am planning to make these kind of tutorials along with the Sparks. So, it will go online for all of you to use, but for now we are going to continue sharing them on the same drive. So, because of which, if you notice anything or if you come up with a nice modification which you think is useful for others, please do share, and we will host them with attribution to you. We will say that this code came from so and so, and we will put it there. Okay, so there are 4 things. Which one? This one, the one where I showed you the document. Yeah, it's actually I use a IDE called RStudio because I teach students R, and RStudio allows me to use knit R to mix code and this thing. You can mix. There is something called web, which is what Kanut used, but I think that is for COBOL because he, I think, wrote that program in COBOL. There is one called C web, which is for C programs to mix with documentation. Okay. But this one is R. There is also doxygen, yeah. I haven't used so much, but Mohan probably can comment because he is supposed to write the documentation at some point for our software that we are developing using doxygen, yeah. But I don't know, doxygen also has the same idea, but I think it will give you in many different formats also, HTML and PDF and so on, yeah. Here also it is possible, by the way, to generate HTML documentation also.
Doing a similar thing in Jupyter Notebook would also work because there
okay.
we have different lines for codes.
I don't know if Jupyter allows you to write equations.
I think it's very similar
to tech.
inside.
Okay.
So like equation thing I don't exactly.
So when I document, like when I do this documentation, I also need that, right? I had a, okay, so let me see, not too many equations you do, but there are some which you want to then get. Here for example. So, it is basically tech, okay. I am teching, okay, and in between the codes will come like this. So, all these f of x minus infinity to x f y dy kind of things, I find it easy to write, but I have found that it is like mother tongue, okay. I learned tech, I feel comfortable, but I know that many of you will feel comfortable with Jupyter because you have been using. So, there must be option to use, but this is what I use because I find it to be very easy to do stuff. Some error function also should be there somewhere here because the area under the Gaussian is basically error function. Yeah, I don't know. So you can make more complicated equations, etc., in this fairly easily. That is what I. Yeah, I don't seem to have more equations than this anyway. Okay.
Sir, so like here for the equations wherever you write or the text whatever you write.
It is tech.
Yes,
Ah.
yes, like it is tech, but I am saying that those things are written as parts of comments in your IDE.
No, that is what I am telling. Actually, I open a tech file. And I write whatever I want to explain, right. You have seen there, right. I mean, there is this book you read and random number, and this is how I do integration and so on. So, basically like you would explain the program to a human, that is how you write the document. So, you are actually generating a text document. In between the document, wherever you explain, for example, okay, this is how you do a random number generator, you can put a code line by putting a specific markup saying that this part is part of the code. Then there are 2 compilations. One compilation is to get a PDF file which is human readable. The other compilation is one where it generates a machine readable C file or tech file or R file, whichever. Okay. And as you are writing this documentation, like you can do with other code, you can also open and run all the chunks. So, it will put together the code and run the code. So, the idea is only doing this business, that it allows you to write a text file and it allows you to compile, get a PDF, or compile, get the code, debug, whichever, and keep going back and forth. But the philosophy here, generally philosophy is write the code and put the comments. The philosophy here is write a technical document, put code in between. After explaining, that is why, I do not know, have you seen the tech book anytime? Where Kanut explains what the tech program is? It must be there, our library. I mean, I don't, it's costly, I don't think people own it. This book is there where he explains the tech program which is used for. So, that book is written using this web. And he developed this as he was writing tech. So, you will see some 10 pages he will explain, about some line or some spline fitting you should do, or why, which optimization you should do to make it look good and so on. And then there will be a piece of code which implements this. Okay. So, it is based on that philosophy. So, here you do not write code, you basically write only a text. Code happens to be incidentals. Nice philosophy. He did not take off like tech took off. So, he himself is surprised that so many people use tech, and I think that is because of commercial interest. Previously, you have to typeset and do lots of things, but now that is done by us for free. So, all journals like tech and so on. This way of programming that he introduced did not take off, but this is not the only way. I mean, there are, I do not know, there are many programming styles. There is some agile programming, pair programming and all that. In software development, if you go, people talked about all these methods of programming, and there were recommended practices and so on. I do not think any of that has taken off in the industry, but I find this philosophy for technical software that we write to be very useful. Okay, so let us start with icing. Icing is a code that I took from the Sparks example file itself. The only modification I have done is to dump VTK file so that we can visualize it. I have not done anything else. So, you can see the icing, Sparks icing tests on generic lattice. There is a seed, so that the same random sequence will come about. You can change the seed, so you will generate a different instance or experiment. And the app style is icing. I will show you next one. Icing, I told you, remember icing is where we have this up spins and down spins on a lattice. So, you have up spins and down spins. Are equivalent, I mean non-conserved. So, here you randomly flip, right? That is what is being done, and this is called Glauber dynamics, I told you. So, if you go to Sparks manual, it says icing basically implements Glauber dynamics, okay? And exchanging is called Kawasaki dynamics. It is also possible to do app style, you change it to, in this they call it diffusion. So, if you change the app style to diffusion, that is basically Kawasaki. So, Glauber and Kawasaki are dynamics. I mean, do I take a random site and flip, or do I take two sites and exchange? That is what, and the algorithm is Metropolis in both cases here, I think, at least that is how I remember, which means if the del E is less than 0, they will take it to be 1, they will accept it with probability 1 because energy has decreased. If it is greater than 1, they will take it with this exponential minus del E by kBt. So, they will take it with a probability. So, they have to generate a random number, compare that random number with this quantity exponential minus del E by kBt, and if it is less than that, they will accept. If it is greater than that, they will not accept. Okay. So, that is algorithm that is called Metropolis, but Metropolis need not be the only one, and Ferdi has shown 2. There is also another one, there is another book, nice book called Modeling Microstructure Evolution. It is a set of articles One of them is on Monte Carlo written by Mark Miodownik. There he shows that one of the transition probabilities that you can assume is 1 minus tan hyperbolic delta E by kBT or something, some symmetric one. Yeah. So, that will be equivalent to this ES minus E1 or something similar, because tan hyperbolic is 2 exponentials, exponential plus x, exponential minus x by exponential x and exponential plus exponential minus x, I think. So, you can think of it in terms of these exponentials. So, there are many different algorithms that are possible. Okay. So, when we say metropolis, we mean a specific way of choosing the transition probabilities, but that is not the only way. And like Ferdi also mentioned, it is important to know for what purpose you are doing the MC simulation. If it is equilibrium, metropolis works. If it is kinetic, then you have to be careful about the methodology, like you are doing Kawasaki or doing vacancy and so on, and how you are choosing the transition probabilities. And that is where the next part of this lecture, where I want to talk about residence time Monte Carlo, which is one of the special cases of kinetic Monte Carlo, where we want to make sure that the simulation proceeds in a fashion where we can evaluate the kinetics, how fast or slow the processes are happening. When we say equilibrium, what we mean is we do not care, we just want to know what is the final state, how it is reached, did it reach it through a really physically meaningful way and so on, we do not care, that is equilibrium. But if you want to follow the dynamics, in this case it was for looking at the ordering kinetics in the Na3Al for L12, and there were some interesting results also, but probably I will not talk too much about that part, but I will show you what the residence time algorithm is and what it means. And I do not remember now, but somebody, I do not think he is here, maybe he is Ajay's student, who was asking how these numbers are chosen, like bond energies, how they are chosen and what their units are and how they are non-dimensionalized or scaled and so on. At least one example I will show from this paper that I have. Anyway, so this is in 2 dimensions, and Nagarajan has shared some parts models in 3 dimensions. So, I will show an example, but I am showing you a 2-dimensional example. It is a square lattice, that is what SQ means. Because it is a square lattice, it has only 4 neighbors in 2D, that is what 4n means, and 1 I think is the lattice distance, right. Okay. So, region, create box, create sites are common, like you have done in LAM. So, we generate the lattice and we populate it, and set site range. What does that mean? The sites will be populated either by 1 or by 2. If it is parts, it will depend on how many variants you have. Sweep is random. Okay. So, you want to give a site up or down, 1 or 2. In parts it could be much more. You can go from parts model, which is a generalization of the Ising model. You can have several, maybe I mean grain growth, we will show you an example. You can have hundreds or even 100,000 different.
Of an alloy, 1 is A atoms, 2 is B atoms. If you are a ternary alloy, you put 1, 2, 3.
So, how you are populating? What are the different? And these 2 are the sweep and solve style are commented out there, but sweep random is what we have been discussing, that you choose a random site. I think raster is methodically it goes through, like Ferdi was saying that you can take and you can think of going lattice site by lattice site and do things, but you can also do it randomly. I do not know what sector means. Nagarajan, do you know what sector means? Okay, you have to look up the manual. I do not know what sector does, and you have to have a model for your energy, and this is using a model called energy. Okay, and I will also show you there are other ways. So, there is Sparks can do this kind of rigid lattice, it can do off lattice, that means like a liquid, particles can be anywhere, so there are different styles of evaluating energy, and I think in this style it just calculates the number of nearest neighbors, how it changes. The Hamiltonian is directly a function of that. In Ising model that is so, because all that you are worried about, now these are statistical models where you only need to know local information, globally something will happen, right. Every spin has to know only its nearest neighbor spins, because of which something will happen at the larger scale. Okay. So, because of which you only need to have a Hamiltonian. This is true in, I think the theory is called Heisenberg theory for magnetism, where he introduces the exchange term in the Hamiltonian, where the electron-electron interaction at that scale will then give you magnetism, I think.
Heisenberg magnetism, I think, is the then feeling there's a majority and minority bands.
Oh, I see. It's not a Hamiltonian that he introduces, where he introduces this exchange term, and that is sufficient to get magnetism. Right. That is Ising magnetism. Yeah. So that is the Hamiltonian that we are going to use, that only nearest neighbor and like neighbors, unlike neighbors you count, and unlike neighbors are costly. So you are basically trying to reduce the unlike neighbors. So if your flip change will reduce the unlike neighbors, the system will choose it. Modulo the temperature which is entering through your exponential minus del E by kBT. If you make that T to be very large, as you can see exponential minus del E by kBT is going to be a very small number, then in general you generate a random number that will be larger than this number that you generate. So you will also accept these energetically unfavorable flips. That is why you will lose magnetism at higher temperature. Okay. So without that, if you are just looking at energy point of view, the energy will be just unlike neighbors that it counts.
So what does this GIAN style by energy, what is it exactly do?
It just counts the number of unlike neighbors and gives that as the energy. And there are other ways of giving energy. So if you read the manual, they will tell you what are the ways. On lattice, off lattice for different ones. For example, there is linear, there is some non-linear, right. Freddy was showing that EAB minus EAA plus EBB by 2. If I want to introduce that, there is a way to do which probably you should try as an exercise, because all that it does, Sparks by itself does is only to count the nearest neighbors, and it will tell you how many like and how many unlike. So you have to write your energy. Ferdy mentioned this also in one of the earlier lectures, that you can tabulate, right. I can say if I have an A atom and if it has 3 like neighbors, 4 like neighbors, 2 like neighbors, 1 like neighbor, 0 like neighbor, I can tabulate the energy. Similarly for B, I can tabulate the energy. Then I can write, I think it is called E coord, that is the comment, that is a command. So you can give the energies and then it will calculate energy accordingly. But this one is Ising model, so it only needs to know the number of unlike neighbors. Oh, I see, okay.
This is diagnostic calculator, I'm just checking the manual here.
Ah, okay. Okay, app style Ising gives the, no, but energy model, yeah, maybe Ising includes the energy model. But in the documentation it is given how to, for example, if you want to change this energy model, linear, non-linear, and in non-linear you can give E coord, all that is given. Okay. And stat sets, how many times once you are going to write the data, and we are going to run 1000, so every 10 steps once I am going to write, and the only 2 lines that you see there, dump VTK, dump modify was written by me. That is just to take the data points and plot them using paraview. That is why I am writing in VTK style. And if you write VTK, it is essential that you give dump modify, and that sort is needed, sort ID is needed, because if you do parallel, then different processors will be there and the data does not come in nicely sorted way. So, VTK is written in a fashion in which the program cannot read. So, it is, if you use dump as VTK, you have to dump modify. This information is there in one corner of the manual, that is what I am saying. I mean, it is difficult in this manual because you have to do little bit of search and it does not give full examples, like for example, it does not say okay VTK, let us look at one example and this is how you do, that is not there. After that there is also this other thing. So, initially because it was 2D, I was using VTK some 500 by 500 and it would not print, and later there is some other place where it says if you are in 2D, you still have to give the third dimension, give it as 1, okay, that information is there. So, that is why it is 500, 500, 1 and 0 and 2 is the range, because my site range is 1 and 2. So, the minimum low and high for what values you can take at every point, that is 0 to 2. So, that is how you dump modify, and dump the label for the dump is 1 and VTK is the format, and every 10 steps once I am going to write and they are written as my.vtk.star. So, which means my VTK 10, my VTK 20, etc., it will go on, and what it prints for every point is the site. What is site? Site will tell 1 or 2. At that site what is the spin you have or what is the type of atom you have. And VTK I think can only dump 3 things, site, DN and RN or something like that, or NN or something like that. But I could not understand from their documentation, at least in a cursory reading, what the DN and RN meant. I tried dumping them and it complained, the program would not run anyway. But site runs and it gives spin. This 1 and 2 are labeled as spin, that also you will see. I will also show you the VTK file. I had to, for one more reason, I will show you that you also need to actually look at the VTK file to plot. Yeah, because the code had stats 10, but I added these 2 dump, I mean, because of which maybe stats hashed out also it will work. The original code only had stats, it had no dump, it will only write to the screen, but the dump I added, because that is the range. I said up and down spin and they are represented as 1 and 2. So, at every site the number that it can put ranges from, no, it ranges from 0 to 2, it is a number between 0 and 2, it is either 1 or 2. In fact, upper limit also is not inclusive. Suppose if you use a parts model, at the beginning you might have 1000 grains. You have to still give the range as 0 to 1000, but as the simulation proceeds the number of grains come down. Maybe at the 100th step you have only 800 grains, it does not matter. In your entire simulation what is the range, that is all you need.
So here this 1 and 2 is basically giving a identity to the upspin and downspin.
It depends on your interpretation. Like Ferdi said, you can say that those are A and B atoms. Yeah. It is a number which you identify what is there at the lattice width. Okay. You can interpret it as up and down spin, which makes sense because this is the Ising model, but Kawasaki also I will use 1 and 2 only. There I will interpret it as A and B, right, or A and vacancy, pure material in which you have a vacancy. So, whichever way you want you can interpret, but it is just a number that we use to identify these states with. Okay. That is the total run, yeah.
Total run as in, because when we talk about Monte Carlo we usually say it's cycles, or
Yeah, I am assuming that it is MCS. Yeah. Yeah.
So this app styles,
Huh.
we have how many in the Spark?
Yeah, the manual gives, I will show you app style, I think some 15, 16 of them are there, but we will show Kawasaki, which is called diffusion there. We will show parts that Nagarajan has used, okay. But the manual lists all of them.
This is attributed to different types of physics.
Yes, what problem you want to solve. Parts for example is for grains, that you have more than 2 states, it is no longer icing. Okay. Typically for grain growth, each grain you will give one number, but if you use a conserved order parameter, because parts is non-conserved, if you use multiple but conserved, that will be equivalent to a multi-component alloy, because each one will represent a composition, A atom, B atom, C atom, D atom and so on. Okay. So there are several, I mean there are
Grain growth, it is the
parts. I will show the parts example. I will also show the thermal gradient, I mean all this comes from Nagarajan, how the grain growth happens under thermal gradient. So on one side you see large grains and the other side you see small grains, because there is a gradient in temperature in the, I will show you. Is it okay? Yeah.
Sector should be to enable the parallel simulation.
Which one?
Sector.
Ah, okay, that is for parallel simulation. Okay. Yeah. Yeah, I was able to run both parallel and serial here. Okay. Running the code is fairly easy. Okay. So, let me first run the serial and show you. Let me first remove all the, because this does not take much time to run. Let me also, so this is all you need, this is all you start with. Okay. So, first let me run serial and you give this. So, you take the input file and you are giving it to the code executable.
Sir, why are you giving VI here?
No, sorry. Okay. If you change the stats number, what it is writing here will change. Okay. Okay. So, now you can see there is a log file and all these VTK files, and as usual please do read the log file, and log file will be like, okay, we gave the seed, we gave the style, we gave the dimension, etc., and then when we said box, create box, etc., it is created, so it gives some information and so on. So, it is interspersed with your script and what it did, exactly like lamps, right. So, you will get all that, and then whatever it printed on screen also is there here, so that you can have access to this data later if you want, and then some time information, how long it took and so on. You can also do this run in MPI. I will show you two examples. MPI run minus NP4, this computer I think has 8 processors. So, I can run with 4, okay, slightly quicker than the other one, I think. We will look at the numbers, then only we will know. Yeah. So, how much is the wall time does it give? I think whatever is in the bracket is the, so here it is 65 and here it is 92. Okay. You can also give, suppose if I give 8, does not run because I do not think my computer allows all the 8 processes to be taken over by this. And for that there is a command which Ferdy also showed the other day. So, you can say I think minus over subscribe, and you can see that in the last line of that message it is there, right. You can see here, right, 3 lines above it says you can use minus over subscribe option to ignore this and so on. So, you can do, then it does. I do not know how much advantage it gives, but we will see. 92 to 65 we came, and I am assuming that this will also be probably 60, 62. That is. Huh? Okay, scaled well. Okay. So, if you have multiple processors, you can exploit them, you can run your code faster, it is possible. Fine. So, we can look at the log, and then you have all this information. I do not know where the processor information it gives, probably it does not. Yeah, it does give loop time of 20.1202 and 8 processors, you can see. Okay. So, okay. Now, I want to visualize this. So, the first visualization I will show for this and the Kawasaki is paraview. Okay. So, in paraview, now I want to open this file. It asks what reader it has to use. Okay. Now, this is where I said it is useful to go look at the files themselves. The top line it says XML, right? Okay. So, now I know that is there an XML reader here? There is an XML image data reader. This is the reader I have to use. Even though I set this reader as default, it does not work, which is good because I can show you how it works. Okay. Nothing happens. So, okay. Then what you do, you see this green apply, you say apply, okay, it shows something. Then I need to change here the representation from outline to surface. Then I need to say coloring is according to spin. Now you see that I have got this. Okay. Now there is this arrow on top. If I run this, this is VTK 0, my VTK 0, and then in 10 it will keep moving. Like Ferdi showed in his case, it was the Obito was also doing that, right? It was jumping from. So, this will also do the same thing. This is icing, and you can see coarsening of both types. The interior blues go away and the outside reds go away and so on. Okay. Fine. Okay. Okay. So, it still complains about this some Python module, do not know what it is. Anyway, does not matter. So, let us go. Let me show you Kawasaki. This is going to be interesting. I am not going to remove the VTK files because it takes for a while to run this case. So, I will just show you the code. So, you can now see app style is diffusion, that is a Kawasaki. When you say diffusion, you have to tell how the energy is calculated and what is the mechanism. I think you can also suppress. So, you can suppress hop and something known as Schwabel barrier, which is important in some thin films. So, we will not go there, but you can give different mechanisms of what happens to the vacancy that is supposed to move. But I am going to assume linear diffusion, which means it will exchange the atom with a vacancy, and I am going to say linear, which means it will still count the like unlike and use it. you can give nonlinear, and if you give nonlinear then you have to tell how the energy is calculated, and for that the command is ecoord. So, using ecoord you can also calculate some EAB, EAA, EBB etc., because now it is going to run just a atom and vacancy. Okay. So, the vacancy where is it sitting, surface or interior, depending on that number of broken parts are different, and that just it is going to do. The only difference between this and the previous icing is that this is Kawasaki. It will not randomly go change a vacant site to a site with atom, that it will not do, or it will not take a random site and make a vacancy there, it will not do. The composition will be conserved, that is all it is doing. So, but you can make it nonlinear, you can put ecoord and you can get whatever EAA, EBB etc. you want. This part of the manual you can go read and it tells you how to do, and you can put off for the energy, and that is because if you want to do some other program for something else, and you can also do off lattice, and for that you have to again give energy model in some fashion. Okay. The rest is the same, it is a dimension 2 and the box etc., and sweep is random and sector S, and yeah, it will print energy, and temperature we are keeping at 0, you can change that also and see what happens, and I have the same VTK style, and this time I have printed 10,000 because initially I ran and nothing happened.
What is temperature 0?
Oh, temperature you can change, or it is like 0 Kelvin, it is not really doing, it will accept all the exchanges that you are giving. It is basically minimizing for only energy, it does not care about the entropy part. Okay, now let us do, you now know the drill, I open and it knows the right directory because I am calling paraview from that directory. Okay. So, that is how it knows. So, it asks which reader, now I know I am wiser. So, XML reader and apply, okay. And solid color I will change it to spin, and outline, okay, last time I showed you surface, you can put volume also. Okay. So, there are very different ways, surface with edges, right. This is similar to what Ferdy was showing, except that here they are all square and what Ferdy showed was circular. So, there are options you can do. There is also one where you can put points. Okay. So, there are many options. I finally found that surface looks nice, or surface with edges looks nice. So, we can do one of that. Let me do surface with edges this time, and I run and you will see what is happening, and that is very interesting. Remember, red is like an atom and blue is like a vacancy in this model that we have. Let me start again and you see what is happening, right. It phase separated, it went towards length scale. After that there is not much that is happening. I mean they just keep going back and forth, and so really there is no evolution that is happening. Okay. Now you can change the temperature and see what happens, but this code takes some time. I am going to share the code, so please do go back, try to modify and see what happens and so on. So, these are the two with paraview we have visualized. Now, let me show you the other two scripts that came from Nagarajan. One is parts and the other one is parts with gradient.
Just one question.
Yeah.
Could you change the lattice to triangular lattice in spaces?
Square and triangular are allowed, I think. Okay, let me. It actually tells you a line of the code where it encounters the problem.
Okay, it will not guide
For example, I could not get a dump image working because it told me that dump image.cpp line number 135 or something, there is a problem. And there I go, I see that if this is the condition and if not defined, exit with this error. That is all you get. So, the manual and the code is not really as helpful as LAMPS. Okay. So, that is the problem, and that is probably the reason why it is not widely used as of now, but I am assuming that like LAMPS was some n years ago and now this will also improve. So, probably we have the early mover advantage. You learn now, you will be the boss at that time. So, lattice you wanted to, yeah, try I can give, and it does not need any number mentioned. Okay, let me try. Dump PTK requires regular lattice sites. This is not a very neat way because it prints the ppm files in some strange orientation. But at least for our purposes we will be able to see.
I did not see what the problem just was.
For the VTK?
Yeah, the sorting or?
I don't know. So, but the manual does say that if you want VTK then it requires something, or for triangular probably it needs something else to be done. It is not clear what it is. But even though the manual is not great, the information is scattered, it still is helpful that with some effort you will be able to still figure out. I mean, it is not completely. Okay, just a second. I really do not want to run 10,000 and that VTK does not really need periodic boundary conditions, right? It just needs the site and it can flip. So, in principle that should not matter.
Also, I did not see where do you define the
This is what I said. I mean, this one gives me file like this. I mean, of course, it is phase separating, but this imaging is really not very nice. Yeah, this is the default output. You can save it as a ppm file, but yeah, it's not great. Okay.
How do you define this the exchange energy? Or?
So, it only counts the number of like and unlike neighbors, and this is the energy. That is the linear model. You can change it to non-linear, then you can give the coordination number based energy, like if 4 like neighbors, 4 unlike, and combinations you can give. Like you said, it is a table basically, but it is given E coord some number of neighbor and energy and so on. So, it is given as a, that is explained here in the oops, sorry, this is not my documentation. Yeah. So, you have to give E coord and coordination number and what is the corresponding energy. So, if it is square and if you have 4, you have to give E coord 4, E coord 3, E coord 2, E coord 1 and E coord 0. That is how you have to list. So, they say that sets the energy, and typically n max plus 1 value should be specified by using this command 1 or more times, with n varying from 0 to n max, where n is the number of nearest neighbor sites for each lattice site. So, that way you can change, but as of now it is only counting the number of unlike neighbors and trying to minimize it. So, which is at some level phase separation.
Yeah. Corresponds to epsilon
Yeah.
plus 1.
Yeah. So, okay, so it did run. We can take a look at the 1000th image. Probably it is also slow because I was writing this every step. Yeah. Doesn't really evolve that much. Yeah. I don't know. Okay, try this out, and if you have any ideas, please do come back to me. Now, in parts, no different. Have a seed. Now, abstyle has become parts, right? Diffusion is for Kawasaki, icing is icing, and Nagarajan now is doing in 3 dimensions. Simple cubic lattice, how many neighbors? How? Why are there 26 neighbors? By the way, what is parts 100? There are 100 orientations. That is why sites range you can see 1 to 100. Okay. Simple cubic in 3 dimension, how many nearest neighbors you should have? Right. First nearest neighbor is how many? 6. And second nearest neighbor how many? 12. So, and then third nearest neighbor must be 8, we are getting 26. Okay. So, anyway, so sweep is random, and again it is dumping energy, and I think Nagarajan is just using dump, and okay, there are 2 diag styles. I think it prints energy and also prints some cluster information, and it is run for 100.
Sorry, where here do you give, or where do you define the energies? Or
This is also unlike, because it's a grain, it's a icing generalization. Parts as is does not have anything other than unlike neighbors.
yeah, but
So,
if you go to higher order neighbors, I mean, the second neighbor should have different energies than the first neighbor.
I don't know how it calculates that.
So they are all.
Yeah, they will all be. I don't know if there is a normalization done for the fact that yeah, Hamiltonian representing energy is sum j delta ij. Yeah. Yeah.
all the,
Yeah.
regardless the distance.
It is distance, it's giving the same weight basically. Yeah. Okay, so let's run this. Now our favorite is to oversubscribe and this is very quick, okay, but the next one is not, so that I will not run. I think Nagarajan's code is there, I am only going to show you. Now this time we are going to use Ovito to visualize. Ovita again I downloaded and compiled, okay, it is not very difficult and fairly easy to do. So you can okay. This I think the other day also I showed. So the different views, top, front and side and perspective, all views you get. Here also again if you just if you, there is this in the bottom there is this, you can go, you can just go here for example, okay, you can go to this for example, or you can just run the movie. Okay. Here also there are possibilities to add modifications and visualize and so on. So we will have a session, I am slowly introducing and you are seeing more than what you saw last time, ParaView for example, but we will have a session. Basically because I am still not able to put together a complete this thing, which where I wanted to show all this common neighbor and this thing. So we will try to put together and have a session.
Nice option, you can slice
Ha.
under add modification at the top, and there is slice somewhere in the middle.
Here.
Right. And now you can just look in the middle, or you can just cut out a slice. I mean, here it's not perfect.
Normal shall I put as so it has already sliced at 50. Okay. Okay, or you probably if I put normal slice along 1 here, 0 here.
Okay, press return.
Yeah.
And you can also cut out a layer if you take the slab width.
Uh-huh.
No, the lowest one. Yeah, okay, do that.
Huh.
No, the slab width.
Left.
No, slab width.
Slab width. Ah, okay. You are saying okay. I can give the slab width to be
5 or so.
yeah. Okay. Yeah.
This I think you can shift through. To get
Make it go through. Oh, I see.
Yeah.
I see. Okay.
just by using this up and down arrows.
Mm-hmm. Which arrows, Ferdy?
In the slab width. On the
Slab width? Huh.
right side.
Ah, okay. So you are saying I can go like this.
I don't understand what they use for the step width there. Sometimes it's 1, sometimes it's some.
Yeah, it's 0.1 going here. Yeah, okay.
The cube is getting chopped from the top.
That is because I have given 1, 1, 1.
When you change the width,
Width because it will go and then it is bounded by the cube. Yeah.
Sir, like this thing that you are showing, sir, it is kinetic Monte Carlo.
This one? This is parts. It's not kinetic.
in the
That is, you can't take the time and take it to represent the grain growth time. No. But sparse can do kinetic Monte Carlo.
I mean, in the sense that visualizes an evolution of the system towards equilibrium. In this sense, it is kinetic Monte Carlo. And I think it was also not fully converged. Yeah? I mean, you saw that the energy was not reaching equilibrium in this
This one.
print out, yeah.
Huh. This is a very small system and only some 100 steps we ran. So.
Yeah,
Yeah, here.
here this energy
Which ensemble?
Hmm?
This Monte Carlo is in which?
This is rigid lattice, right?
So you are just doing.
No pressure. We have a constant temperature, constant number of particles. Can assume that because we haven't put any pressure term, the pressure is 0. So. Volume also is constant, so it's a rigid lattice.
Constant particle, I mean the orientation or the value of the Potts variables changes.
Changes, yeah.
If you take the Potts variable as indicator for the, if it is in 100 ternary alloy, this would mean that some of these species disappear.
Yeah, we are doing, we are not conserving, so.
Yeah.
Okay, so this is in gradient. I'll show you the visualization. You will see what it is, but the result is generated by running in parts temperature gradient, not mobility gradient, but the mobility gradient is also possible. So you can see that there is a periodic in X with temperature gradient, that is also possible. So you can see several in files, but what I am going to show you is generated using the in file in parts temp grad. Okay. Takes some time to run, that is why I am not running, but it is fairly straightforward to run in the same fashion like I ran the other ones. Even data here takes time, you can see that is spinning here. Bottom also, yeah, I did see, you can see that it is.
Those the other views, there's this top and view side.
So,
I think if you double click on the perspective or so. This button thing there below this number of,
this one?
yeah, one further, I think. This where the view, yeah, here to the right.
To the right?
Yeah, it's here. Somewhere you can, one of these three
Allows you to, yeah. I know, I mean, some of them, Arjun for example, when he does show me, but I don't. Okay, so let us try to, it takes time, yeah, so, but one end is at high temperature, other end is at low temperature, so you will see grain growth happening more on the higher temperature end and the less grain growth on the other side. So that is what this code does. So this is also probably an example script that is there in, yeah, so this is an example script that you can go take a look at. Yeah. So you will see grain growth happens, I mean by the time you reach 5 or something, these have become really big grains. On the other end, they haven't grown so much. Okay, so this is as far as the sparks is concerned for today. Okay. What I want to do now is to tell you about this residence time Monte Carlo. I am not going to give you the implementation, okay, but you have the simple Monte Carlo code that I gave. So you can go try to modify it and see if you get the thing. We have time or?
I don't know, it's 5 o'clock.
Okay, so what do we have tomorrow?
Just checking.
Yeah, we can decide based on that whether we will, because I do want to spend some time explaining the. So then probably resonance time I can move the elastic stress to later. And
I have not that much left. I have one chapter on nucleation, precipitation reaction, and then we have coupling in DNT.
Yeah. coupling MDMC, we have some interesting things to show. Okay, in that case we can do tomorrow. So, I want to spend some time explaining this residence time Monte Carlo algorithm. In fact, it is a paper from Abhi, my advisor, Ferdi and Martin, their postdoc advisor. So, this is a paper from 96, 97 in Acta Materialia, where they explain very nicely the model and the implementation, and it also led to some interesting results. At that point there were some information in the literature, this model showed that that is not correct, and we will not go into the materials details, material science details, but to the extent that we want to understand what this problem is, what is the ordered structure and what is it that they are trying to model, what is the kinetics they are trying to get, and to answer the question how do I get these parameters using a simple, they used a very simple bond breaking model. And there is also some other interesting, like Freddie talked about the ordering, but in L12 they had to use for the AB bonds first nearest neighbor and second nearest neighbor different signs of energy, and that was essential, otherwise it will lead to some frustration effects and so on. So, I want to spend some time giving out all those details so that you can appreciate what the problem is. The code itself will not be very difficult. I mean, you have seen my code, it just requires instead of generating one random number, two random numbers, and there is a way to use that information to keep track of the time that one random number is used for that, the other random number is used to identify which is the jump that is happening into the vacant site. And using these two, this is an example of a kinetic Monte Carlo, this is called residence time Monte Carlo. So, it will give you the correct time evolution also when you complete the Monte Carlo. Ferdi also I think used some GCMC there to get the phase diagram constructed. So, probably you will talk about phase diagram construction and then that will make sense. I am not going to talk about the phase diagram part, I just want to tell about the algorithm. It comes from the paper that Ferdi referred to earlier, Gillespie's paper. So, this formalism is modified from there for this purpose. So, we will do it tomorrow. I need an tomorrow, Ferdi, you will do in the morning. Yeah, then tomorrow afternoon I will do 3 to 5. Okay. This and probably capillary fluctuation theory also requires some, I mean if you want me to, if you want to do alternate, I can do capillary fluctuation theory, I can show what the idea is, and afternoon 1 hour and then I can do. Residence time probably I will do tomorrow in the afternoon, because the other lecture I have is more sort of StatMech. How does one get anisotropy in interfacial energy by doing an MD simulation? I mean Ferdi did refer to this, that you can have a solid melt interface and allow it to fluctuate. By measuring the fluctuations you will be able to tell about the interfacial energy anisotropy as well as attachment kinetics anisotropy at that interface. Like we showed for the iron case, you can now put different interfaces and measure this anisotropy, attachment kinetics for example. So, those kind of things you can do. So, I will show you the formulation for that, and then I will show you the residence time Monte Carlo. For choosing whether going to accept or not, we are using Metropolis here also. Okay. It is very difficult to get the, see kinetic Monte Carlo requires you to know all possible ways in which things will go.
Input we gave the number of orientations.
Right.
So that is fixed.
Yeah.
So it has to conserve that number of.
It will not conserve, because this is Ising. Parts is a generalization of Ising model, and if you start with some number of grains, it is not necessary that they have to remain in physical case also.
They can dissolve completely also.
Grains grow, right? When you say grain growth has happened, the total number of grains will come down and the average grain size will increase. So, grain they do not have to conserve. So, it will go find a random site and change its orientation to one of its neighbors. Yeah. and it will do it based on the energy. It will calculate this number of nearest neighbors, unlike neighbors, and if this change reduces the energy, it will accept that. That is how one of the grain is growing, the other one is shrinking.
All three whatever we today discussed, they were almost.
Except for Kawasaki, the second one that I discussed. The first one icing and the other two are parts, they are one family. They are global dynamics, which means they do not conserve the order parameters. The second one that I showed, Kawasaki, that conserves. There the number of A atoms or whatever you took will remain the same throughout, and it was also printed, you could see in one of the.
Sir, so what is the difference between the three simulations that you showed here and a kinetic Monte Carlo?
Kinetic Monte Carlo is one, tomorrow I will show you residence time Monte Carlo, where you will also keep track of, for example, when we say kinetics in this case, for example, we mean the time. If I do a simulation and if it gives some time, can I map it with the actual process time? If I do that, then it is kinetic Monte Carlo. Okay.
Sense of physical time.
Yeah, to do that, there are two things, like Ferdi said, you know, you can't take random atoms and move and then expect that kinetics will come out right. Then you have to use physically meaningful processes. In this case, what I am going to show tomorrow is a vacancy kinetics. We introduce a vacancy, we make the vacancy hop, and we take the frequency of vacancy hops accounted for in calculating the time. That is one part. The second part is in the algorithm. How do we calculate? That is where grain growth becomes problematic to study using KMC, because you need to know all the processes that can happen and you need to know their probabilities at some level, right. Then you will choose, okay, this event will happen with this probability, that event will happen with that probability, so I can add them all up and then I can do the simulation. But if you do not know all the processes, or the processes are too complicated, or there are too many for you to list, then you cannot do a KMC, right, because you do not know all the processes, you do not know all their probabilities. So, how will I put it in the model?
Sir, so like here also we are doing an evolution of this.
Yeah, we are doing an evolution.
But here we are not mapping it to the actual physical.
And you can see, I mean, even with not being kinetic, you still get some information. Like for example, if I keep the same sample and two ends at different temperatures, you will see larger grain growth here and smaller grain growth here. Those kind of things you are able to see. Yeah. But what you cannot get is the kinetics. When we say kinetics, how fast or slow this process is happening, right. Now, I can't do this simulation and expect that, okay, if I take a sample and do this, it will map one on one. That will not happen. When we say kinetic Monte Carlo, we need that information, we want that information. Okay.
So in this case, the time was not there, like time was not there.
So, typically, if you take some number of Monte Carlo steps, larger the number of Monte Carlo steps, naively you might think that you need more time, right. If something happens very quickly, like you saw the icing and Kawasaki, icing just went in no time, but Kawasaki there were these vacancies just jumping back and forth, they were not leading to the microstructure evolution. So, you can see that one process is slow, other one is fast. That kind of broad thing is okay, but when we say kinetic, we want to have a little bit more concrete than that.
So what about the physical space, whether for the grain growth kind of thing, the space which we have, like the distribution of grains what we will see here, whether they are like we can compare it with the experimental things?
Grain size distribution, yeah, at some level, but
But in
yeah.
literature I have said they have pointed out the physical dimensions also, what CA versus MC, that demerit is listed here.
Yeah, CA, but CA itself is not really a physics based model. You have arbitrary rules.
Velocity
Okay.
we plug in from outside, the growth.
So, the right thing to compare would be with a phase field model, because that is also free energy based, and here you have a Hamiltonian which is like free energy. So, to some extent you can believe that if you had the right starting distribution and stochastically it should evolve like real system, provided you got the physics right, there was nothing else involved. In an experiment, if you can control the same parameters that you controlled in simulation, you should, barring finite size effects and things like that, right. I mean, use periodic boundary condition, then this grain becomes the same, then that layer is not valid for your statistics and so on. So, it is a problem of getting proper statistics, doing really large scale simulations and getting. So,
I think it's also a problem of physics. I mean, this spots model to mimic grain growth is, I would say, it oversimplified. I mean, it just assumes that neighboring points should have the same orientation, same grain orientation, nothing else. There's no grain boundary mobility, there's no grain boundary energy, and nothing in it.
Yeah.
And in a real recrystallization experiment, all these parameters control, plus the nucleation of new grains, control the texture which forms, for example. So I would not take this too serious, in my opinion. So just, I mean, that's why I asked. I mean, just two points in the grain should have the same orientation. This first, second, or third neighbor shell. This is what is in the model. That's why you get, of course, the grain growth. If you have a curved grain boundary, then this will move forward.
There are some.
Yeah, in this microstructure evolution book, Meerdonic shows how this rule about unlike neighbors actually captures at some level the information about the curvature, which is probably not difficult for you to see, right. If I have one like this, if this is curved like this, then these points will have unlike neighbors, right. If it is flat like that, it will have some number of unlike neighbors. So, that is what is capturing the physics to that extent that, and this model also has the mobility rigged, for example, but there is really no grain boundary. Like he said, I mean, there is one upspin, one downspin, okay, you will mark a boundary between them. And this up and down spins themselves are representing larger volume of the crystal, right, because they are representing the orientation, they are not spins, they are representing the grain orientation. So, it is coarse grained at some level. So, because of which, yeah, but it is still better than CA, I would say. And our comparison with phase field and MC he has done, yeah, I mean, okay, not bad is what I would say. But recrystallization and things like that also involve other stuff, like there should be a driving force in terms of elastic energy and so on. So, there I would not expect, but grain growth as such, you know, I take a sample with a given grain distribution, put it and then look at it, probably some aspects this will capture.
So, like, it's like I do heat treatment for 1 hour, I get a distribution and 2 hours, so that can be captured with the.
Would be my feeling, provided, you see, that also is tricky in the sense that we are not distinguishing the orientations. We are not giving the grain boundary what type of boundary it is. There is a way to hand put all that. You can identify orientation 1 is this, so between 1 and 3 I will have this boundary energy and this boundary mobility and so on. You can put, people do, then you will get something which is realistic. But if suppose everything is isotropic, okay, it is a soap bubble, fine, it will get. But that is not the real case. So, to that extent, yes, we cannot claim that it will capture, but if you know that, then if you say no, these are not the first order effects for me, that much you will capture. But recrystallization is still a tricky problem, right. There is no nucleation here, there is no strain here, it will not be driven by, we are not saying which grain has higher strain compared to which grain.
And the only driving force is the
Curvature.
curvature. Normally, grain recrystallization is driven by dislocations in the non-recrystallized part, and no dislocation or very few dislocations in the recrystallized part. So, all this is not contained here. This driving force is.
So in Sparks, they call this method as equilibrium article method.
Yeah, it is not kinetic.
Yeah, they use all the parameters
No, that is just that you can get by normalization. You can take E and normalize by KBT, and which is what we have been doing for others also. That does not make, I mean, that is not making it pseudo, that is just non-dimensionalization or scaling, right. So, it is not.
Its spark will not have capabilities to bring more physics about the grain boundaries energy.
It does. For example, you can change the mobility.
There are three different variants in algorithm. If you want to use Gainsey algorithm, you have to use different solver model. So then it will do the Gillespie algorithm, then it will give the kinetics.
Does it also allow to, I mean, if you, in the spots model, if you speak about different grain boundaries, this would mean if you have a pot spin like this and another one like this has a different interaction energy as two like this. Yeah? So if two grains are strongly misoriented, typically the grain boundary has a higher energy as a small angle boundary, for example. Yeah? Is this possible to put it into the spots model so that different?
It does the mobility difference, but I am not sure about the energy.
Yeah, it's an energy part.
But probably using E quad you have to give, you have to list out, because that it does allow. So, if you say one with so many 2 neighbors, 2 with so many 3 neighbors and so on, if you list, yes, in principle it can do.
Yeah, but I mean in the POTS model you have say 100, but
Yeah.
3 different orientations.
Yeah, yeah. That you can do.
The action should be different between these and these.
Yeah, yeah.
Would be essential.
Yeah, that probably would be because it allows for this E quad where you can tell the number of neighbors and then give a table of energies for that. And it allows for mobility. Like there is a solved problem where they change the mobility from a range, and because I think different boundaries can have different mobilities. So
This is clear, that's the physics, but how is it implemented here?
I think they do it like temperature only, right?
Mobility as a function of temperature. So they have a relation, Arrhenius relation. M is equal to M naught exponential.
Okay, but this does not mean that different types of grain boundaries have different
No, that mobile, no. The only driving force you can change by changing the energy.
Because I mean in real systems also, for example, these special sigma boundaries
They will be stuck forever, yeah. So
or small angle boundaries have a low mobility
Yeah.
while high angle.
as far as I know, that is not there in the model. So no, I mean, at least the app style will tell us what is available.
Did you ever look into, I did not look into the sources, it's C code or what is it?
That yeah, please go ahead.
So I don't know how difficult.
This is all C, I thought, Ferdy. So in fact C++, they also use this object oriented thing. I looked at LAMPS also, where they tell if you want to add how you should do and what are the things you have to take care of, and they recommend what is the standard input output you should use and so on. IO stream you are not supposed to use, STD IO you are supposed to use and so on. So there are. So as of now there is a diffusion, icing, parts, relax is for off lattice, and chemistry is for reactions, and these are the only, here erbium membrane and parts with pinning sites. A strain is also there, so probably you can do recrystallization. Per site strain you can introduce.
Temperature gradient is uniform. No? We can provide non-uniform temperature gradient.
The gradient, is it constant?
Design the profile such that
We have the capability to give at each node the temperature, so that non-uniform temperatures can be.
yeah, you can if you want to use non-uniform temperature, you may have to edit the script.
Okay.
Not input script, you may have to edit the code.
Okay.
Through input script, I think you can only give the linear.
One dimensional.
phase field.
Oh yeah, they had, that is probably Tikare, this thing. Yeah.
There are much more. If you look into the sources, there seem to be much more than mentioned in the.
No, the parts phase field is also described somewhere. I don't remember whether it's in the website or in the manual. One place it does describe, but they are not consistent. I mean, you will see some descriptions in some place and some descriptions somewhere else.